So once again, hi, let me welcome all of you to the From Space to Cloud Practical Earth Observation Workflows webinar organized by Cloudflare. My name is Marcin Niemejski. I work as a data scientist here at Cloudflare. And together with my colleagues, we will share with you our knowledge, insights, and best practices taking on combining Earth observations with cloud infrastructure capabilities. Yeah, we grow and share our potential thanks to amazing projects such as Gateway. Gateway aims to create a comprehensive and integrated ecosystem driven by cutting-edge technologies, enabling secure sharing, use, and storage of geospatial data. Today's event will be hosted by members of Cloudflare's data science team, specializing in geospatial data engineering and Earth observation algorithms. Tomasz Furtak, Bartosz Augustyn, Bartosz Staroń, and myself, Marcin Niemejski, once again. So the agenda. We will start with company overview, so you can get in touch with our principles and ideas for a business. Then Tomasz will guide you through our repository and dedicated data discovery tools. After that, I will present my personal highlights of our cloud infrastructure and give you a few ideas how to combine it with your existing pipelines. Then Bartek will share the concepts they worked on their internships with you. And we'll end with Q&A session, but please feel free to ask questions on the chat during whole webinar. Then we will just gather them in the end and answer everything all at once. Or maybe the quick ones will be even answered immediately. Okay, so company overview. Instead of fighting for clients with hyperscalers like Google or Amazon, we decided to found our niche in form of remote sensing data and provide tailored solutions for people who work with large data sets, for people who analyze climate changes, for universities and public agencies. So thanks to it, we specialize in data storage of Earth observation data, processing of Earth observation data, and creating platforms enabling fast data discovery and everything that supports users and customers with their daily work on making basically products out of the Earth observation data sets. So we started 2015. I guess you can see that we are now a very large company. We finished 2024 with 240 people, and now we close to 2045 with almost 300 people. Our highlights of our company's highlights are for sure the ESA projects, namely CDSE, so Copernicus Data Space Ecosystem, where we serve as a storage and infrastructure provider, but also the EUMETSAT Data Lake. So these are two our biggest projects, as well as upcoming Kamila from the ESA, so the National Polish Satellite Constellation, and also a few more in the future. So our ideology and technical autonomy can be described in 4 pillars. First of all, we build our own servers to provide quality that meets our requirements. We do it ourselves. Then on those servers, there's almost 100 petabytes of data, of Earth observation data, gathered from the most successful project, open space project, which is Copernicus. Then we provide within our infrastructure access to the open source technologies such as Postgres, QGIS, GDAL, and OGC standards, just to enable everything. So make sure our users have access to the complete technological stack that they can use in their work. And then we provide the API and various ways to explore the repository, because if you think about over 100 petabytes, you can think about it as a standard folder, but then browsing through this folder makes no sense because the repository is so huge. So it needs dedicated ways to access the data, for example, through an API or through graphic user interface, which in fact is using API, but this is also a very good option for users who prefer, for example, going through the website and not constructing the API requests. So those 4 pillars aims to prepare and provide users for the explosion of quality and quantity of Earth observation data. Basically, nowadays, public space programs provides almost very high resolution imagery, of course, aimed more into the agriculture and climate changes and monitoring of, for example, agricultural fields, and not the more custom solutions. But here is, of course, something that we provide, and yeah. So I guess you can see that there's a lot of strategy going on to make our users freely access this data. For example, we need to provide self-storage as well as with the correct chunking strategy. So everything is built to provide users with fast access to data.
Okay, so I think it's my turn here, Tomasz. So right now we would like to show you some data sources and our data catalog. Which type of data do we have? Marcin already said about the CDSE project, and it also connected to the Copernicus program. So in our platform, CREODIAS, main base is this type of project where all the data are continuously updated. And this Copernicus program is basing on the Sentinel satellites, which are basically core and major part of our catalog. This program is founded by the European Commission in cooperation with the European Space Agency, and gathers, as I said, satellite data, but not only, also in situ data, and also different type of services and different initiatives. What is important in our case, our catalog is constantly changing and growing, because regularly all the data are coming from the satellite to our database, which keep us updated all the time about new data. And it also is important, for example, for crisis management, for really current phenomena that are ongoing in the Earth. Then I would like to really shortly describe you some Sentinel missions. Here in the table you can see that we have 5 Sentinel missions. The main one is Sentinel-2, which is the most intuitive data source, that is passive sensor, which is optical, and also has different bands that I will tell you later. We have also Sentinel-1, which was the first satellite launched in 2014 by European Space Agency, and other 3 satellites that are mainly used for the global and climate initiatives and analysis. All of the missions have different resolutions, as you can see, ranging from resolution from 10 meters until 5 kilometers. So it shows the variety and range of the different data sources, which is really crucial for different type of analysis. Also, as you can see, we have data from 2014, from the beginning of the program. So we have all of the historical data that can be used. It's really crucial in many analyses that need some period of time to be observed. So we have already 11 years of observation in case of Sentinel-1. Then in practice, we can see the visualizations of different missions. We have Sentinel-1, for example, 3 visualizations. First two are 2 different polarizations. On the first one, for example, we can see the Bay of Athens and a lot of ships on the bay. So you can see only on this picture that we can somehow analyze marine traffic because of this data. Also, it's really nicely visible that on the second image that different polarization changes visualization and the characteristic of the objects that can be combined and even enhanced. And that is visible on the first picture where we can really easy and nice visualize, for example, urban areas. As I said, Sentinel-2, so that's the second column, is and the most intuitive data source. So first I have a normal picture from the visual spectral range, but also this data source has multiple bands in which we can manipulate and calculate different indices, such as moisture index, which is visible on the second visualization, but also we can use it in many other applications such as vegetation or snow identification. As I said, other Sentinel missions are more concentrated on the global analysis and climate analysis, and we see the temperature visualization on the third line, and in case of Sentinel-5P, also the atmosphere monitoring and gas spread, so it can be applied to long climate change analysis. Also, what is really important in Copernicus and in our catalog, we have some complementary data sources that I would like to show you now. First of them are contributing missions with very high resolution. They have different type, from optical to radar data, but also it covered digital elevation models that I will show on the next slide. And it's really important because it enables precise monitoring. The best resolution from Sentinels is maximum 10 meters, but in this case we can analyze more local phenomena which cannot be caught by the Sentinel data. But in this case, not only signing in our catalog is enough to use this data. In this case, you need some authorization licensing by the Copernicus program. And I would like to show you some potential visualization and usage. So we can see here that we see a lot of more details on the pictures. We can even analyze single cars and trees, which is really crucial for local analysis. We can also calculate, like in the case of the Sentinel-2, different spectral indices. And yeah, in this case, resolution is varied between 1 meter or even less until 5 meters. In SAR data, all of the collections are concentrated around the ice and Arctic region. So on the SAR data, we can really easily visualize visualize water and ice, which is visible on the image C, but also floods, which can be useful, for example, in case of flooding last year in Poland and in Central Europe. But also we can check information about urban areas, but also morphology of the vegetated areas or crops, which can be led to agriculture statistical analysis. Last, we have also digital elevation models that basically show the shape of the terrain and also sloped aspect and enable detailed flood risk assessment. As I said in the beginning, in Copernicus program, there is not only satellite data, but also some services that are focused on transforming raw Earth observation and in situ data into more detailed and value-added information. So in this case, we have 6 different types of services. In our catalog, we have 3 of them, which is marine, land, and emergency service. And the advantage of it is that we can conduct some continuous environmental monitoring and improve forecasting. And example is, for example, the land cover map of Europe that is visible on the slide. So we don't have to process Sentinel data or other data to get ready data to map different type of areas. Also complementary to Sentinel data, we have gathering of the Landsat data, which is basically sister of Sentinels, but in American version. The advantage of this collection is that we have 50 years of observation, so it's a longer period of time, which is really useful for climate studies and some temporal analysis. And the resolution is quite nice because of the 30 meters. For the oldest years, we have only coverage of Europe, but the latest dates are also global. Filling also the gap, we have a new data set of thematic data that is separate into different domains, such as human settlement, global water and climate, ecosystems and vegetation, digital elevation model again, radar data and land cover. That also enables long-term changes. And here on the right, you have different visualizations of the data. So you can see that they have different resolution and quality, which can be adjusted to your type of analysis. And last, other collections such as SMOS, that is concentrated on the soil moisture and ocean salinity, MERIS, which is a high spectral resolution instrument that is concentrated on ocean color and atmospheric and land surface analysis. And last, the eco-stress thermal infrared measurement that enables plant water stress and evapotranspiration analysis. So that's all about the data that we have, but the most important part of the data is the way how we can access it. So now I would like to show you 3 main ways how to access our data. So first is the CREODIAS Data Explorer, which basically is the user experience platform where you can really easy and fast discover, preview, and access the data. And actually, I can show you really quick some live demo how to use it. So if you log in and use QR code which was in the presentation that I will show you in a minute, you can directly go to this website. And with this button here, you can choose your area of interest. In my case, I have chosen Warsaw area. And here you have all of the data sources that I was discussing. For this demonstration, I can show you the Sentinel-2. If you click it here, you have even more detailed filters such as platforms, product types. Also here from the basic filters, you have, of course, a data range. In my case, it's last week, but also you can filter by different areas of interest and different type of sensors. So also you can copy query for later and use it in other endpoints, but we can click search, and all of the products that are well queried will be shown. And here we have all of the data that are matching our needs. So here we can visualize it and see some details such as which satellite is it, what instrument is it, what type of cloud cover is there. Also, you can put it in the query in the user experience, which is really important in remote sensing analysis, but also you can go even more detailed for all of the metadata that are connected to this product. And in the end, you can download the data that you are interested into. So you can see that it's quite easy even for people that don't know really well remote sensing, but also we have two different options. That is OData API, which is a REST standardized API, which is query based. And in this case, also we can search, filter, and select your products, but in more efficient way, because we don't have to click a whole dashboard about it, and we can download more data at once, which is really crucial, for example, for web applications or different type of analysis that need some more products to be downloaded. You can do it directly in the cloud, and also you have all documentation about this OData API, how to use it in this QR code. And last option that I would like to show you is our new STAC API catalog. That is standardized for spatiotemporal data. And that is really crucial from the perspective also of user, because we can really easily query this data and do it much more efficient. So I have also really quick use case for that. And I will use the Capella data from the thematic collection. And this use case shows how, for example, in the city of Stockholm, we are able to identify urban structure using edge-based analysis, which is really simple. First, you need to log in to our website to create an account, which takes around 60 seconds, which is really easy. And then after using this link, you can directly create your S3 credentials, which are crucial in this case because it enables you to access our database. After creating the S3 credentials, you have to save them because it won't be shown again. Then you can directly put it in your code with other environmental parameters. And here we can finally connect to STAC catalog with our endpoint and query data that we need. In my case, I have chosen a point in Stockholm, and I need to put the name of the collection that I am interested into, and also the geometry. You can also put here much more details and query it more detailed, but in case of the Capella data, we don't have that many objects, so that's easier. But for example, in case of Sentinel data, you can put the cloud cover, orbit direction, or a product type, or even more information, and data will be queried. After running this code, one product was found, what I was interested into. Also, every product in STAC catalog has different assets, which are basically the files, and we can directly access it without downloading all of the files that we don't need. And now we can work on our data. We can load it to Rasterio, change the coordinate system, and crop it to cut the information that we need. And later we can work on the data, converting the SAR image to decibels, normalize it, and smooth it for better visualization and filtering of the information from the data that we really need. And after this couple of lines of code, we can acquire this type of data where it's shown the different buildings in Stockholm. Later, we can put some really easy edge detectors that are well known, Kani and Sobol, that capture different type of edges, and we can easily put it in the code the same way, and also show the final result of the edge detection. And we already can see that major and the most important edges were found of the buildings, but we have a lot of noises still, but it's really easily removable, putting some filters on the small noises, and also closing different parts of the pixels that are basically open. And in the end, we can easily find the morphology of every building. It's not maybe perfect, but in this amount of code, I think the result is quite nice. So you can see that really easily and really rapidly we can analyze and have some output from our data. So
Okay, I can take it from here. Thanks, Tomasz. So let me just quickly jump into my part. Basically, if you have just one raster, just like Tomek has shown, it's okay to run it in Jupyter Lab because it's a nice proof of concept, and Jupyter Labs are very convenient in terms of running Python environment and doing some quick stuff there. But if you, for example, want to move into production, or you want to monitor some area and you need to process thousands of rasters daily, then I guess you should get familiar with virtual machines, which can be very easily run from the Horizon dashboard, which is the graphic user interface for the CREODIAS infrastructure. Basically, you log in, you move to the instances tab, which represents your VMs, and from here you can select basically any kind of a virtual machine, ranging from Windows to Linux, and this machine can be of any size. For example, you can select the amount of CPU, GPU cores, RAM, or storage, and yeah. What's more important, like I said earlier, our repository consists of over 100 petabytes of data, and our cloud infrastructure is built next to this repository. Thanks to this, the connection between virtual machines and data from Copernicus program is extremely fast. And so thanks to this convenient solution, you can just jump into action and start to work with the data without need for downloading it. Also, from my experience, the Horizon dashboard is pretty. At first, it can be pretty confusing because there are so many options, but the process of setting up machine is pretty repetitive, and basically it might be hard to do it only one time. Then it's just pretty much the same, but you just select different flavor, different image, or different Linux distribution. And what's fun, we provide native support for OSGeo Live, so the Linux distro provided by Open Geospatial Consortium. So you can install this. You can select this image. You can set up machine, and you can jump into OSGeo Live, which is provided with basically every GIS and remote sensing software that there is. And also you have quick access to this S3 repository that I mentioned. Yeah, and the other thing is that you should probably think about some storage for your output products. And here I can recommend you our object storage, which is very durable, cost effective, and basically provides you with unlimited scalability. It's perfect for storing EO imagery, especially when the EO imagery is stored in the right format, for example, cloud optimized GeoTIFF. Then it can be really handy to reach out to this data and, for example, extract the interesting information tile by tile without the need for reading whole raster. So, for example, the STAC catalog that Tomek has shown basically provides the assets path to the object storage. So you use data catalog to get the path to object storage. Then you do the computation on the VM without the need for downloading the data. And then to make your datasets public, you push output products back to the object storage, but to your own, but the one that you own, and then the one that you manage. And from there you can, for example, create your own STAC catalog and provide your users with the data, with your data. Another thing, which is pretty much a pretty advanced one, are the Kubernetes clusters, are as easily run as VMs on CREODIAS user interface. You can create scalable managed Kubernetes clusters with the support for, of course, automated deployment, scaling, and operations, which are basically the key things for Kubernetes. It's a perfect solution for high availability Earth observation applications. For example, if you want to host your, if you have some vector data of a volume of big data, and you want to store it in some optimized place, then I guess I can recommend you the cloud native Postgres and its Kubernetes friendly deployments, which supports the high availability mode. And we support Terraform, which makes infrastructure as a code and deploying your applications really easily and repetitive.
So hi, I'm Bartosz, and I would like to show you the first use case of how to use practically the Earth observation data. And it's the detecting oil spill based on SAR images. So the oil spill is very visible in SAR image because it's like it's easy to find it on the image because of the how SAR works. Basically, it sends microwave pulses and measures the backscatter returned to the satellite. And on the ocean, on the water surface, the signal comes basically from waves. And the oil surface smoothens the water surface, and the energy reflects away from the sensor. So that's why on the SAR image, the oil on the water surface looks like a black pixel. So that's the introduction, but why it's so important to find the oil. Basically, the oil spills are actually pretty common. They from ship malfunctions, but mainly from the accident on the drilling ridge, like a Deepwater Horizon. And of course, we have some ways to minimize this oil and clean the water surface, but even the small amount of oil is deadly for any marine life. The quicker we find an oil, the easiest is to clean the water surface. So that's why the monitoring oceans it's really important to do. As Tomasz said before, we can access the SAR images based on the CREODIAS Data Explorer. So if we know the coordinates of the oil spill and the range data, we can filter it, get the data, and then use it to our analysis. But Tomasz said more about this, so let's go to the another part of building the dataset. When we have images, we can create masks of these input images by using any tool, basically, such as, for example, Label Studio. It's the open source tool, really similar to Paint, so it's easy to use it. Anyone can learn. It helps to create the image where we can create a mask of where some pixels means one thing, the others are a different class. But it's really accurate tool, even though it's really easy to use. As you can see here, we have one input image and one mask image. So you can clearly see where the oil is, because as I said before, the oil on the water surface looks like it's just a dark pixel. So we can, after the if we have our part of the building dataset, our dataset can contains a lot of images, but this dataset contains only 15 SAR images because they are really big. It's like million of pixels. So to have anything useful, we cannot use only 15 images. But because the image is the original image is so big, we can crop it to the smaller parts, such as, for example, in this project, 124 per 124 pixels. Why this small image? Because I want to preserve the special context of the oil spill. So yeah, after training the model, I won't talk here about the specific, how the unit network works and the more specific things, but the model works basically like that we have an input image, and based on that, he wants to predict where oil can occur. So basically, on the predicted mask, white pixels should be an oil. Of course, there are some noises, but as you can see on the image on the down left, we see there are on the input image are some parts where we have black group of pixels that are not oil. That's why I chose this to crop this image into images of 1024 pixels per 1024 pixels, because I wanted to train a model and learn that it's not an oil, it's just an anomaly. And as we can see, it works pretty okay. It's really easy use case of how to use OData and how to use the virtual machines, because all of these computations were made on virtual machines, because we need first a lot of space, because one image, one SOR image, it's like 7 gigabytes, and also we need a lot of RAM and GPU, because training machine learning models on images, it's much quicker on GPU, and that's what CREODIAS provide. So if you want to learn more about this project, this use case, a little bit more about specifics like some Python coding, you can visit CREODIAS EU, where is an article about this use case.
Okay, hey everyone. So now I would like to go to talk a little bit more about embeddings. Some of you are probably interested about our datasets, so I will give you some ideas in a second. But first, the point is what are actually embeddings and what you can use it for. So everyone knows probably at this point about foundation models and AI overall, and how we can apply it in geosciences. So for example, we can have datasets around air pollution, altimetry, other data types like SAR, thermal, or just optical data. We can use text to create embeddings. And all this data can be used for specific tasks like classification, regression, image generation, or image capturing. But all this takes time, a lot of storage, a lot of data, and you can have problems with good results even after creating large data sets. So here comes embeddings. So I would like to talk what it actually is. So we have definition that embeddings are vectors in high dimensional space that capture data relationships with meaning. And what that means is someone can ask, so what's the difference between embeddings and just pixels in satellite images? So the most important part is that even though both of them are just numbers from computer, embeddings can capture the meaning behind the pixels. So it's not just raw numbers that computer tries to estimate in some model, but it captures the semantic or overall meaning that can be in that. So for example, how embeddings are created. We can have our satellite image, and we have model that generate embeddings via text encoder or image encoder. And that way we can create a great repository of embeddings that are easier to use for bigger analysis. So I would like to show you 3 quick examples how you can use embeddings. So because this type of repositories can have a lot of data. So here we can see the example in flood in Poland in 2024. So all the dots you can see here are one parts of images, and they are divided by colors on the dates. And the one you can see below are quad score in Poland, where was the flood. And we can see that the images that are similar to each other are the city area that was not under the flood. And when the flood came around 18th of August 2024, you can see in the image on the top left that whole area is changed in the flood, and all the patches that are shown with flooded area are actually clustered together, and all the rest of them are in different space, in different cluster. In Spain, in 2016 and 17, we can see that photos collected via Sentinel-2 were pretty much all clusters together on the top. The colors are purple. But around 2019, the process of drying up of the reservoir actually started around June and till the August, and it completely changes the trend, where you can see on the bottom right that the whole reservoir basically dried up. And the problem was because there is a big big dam that is a hydrological power plant that couldn't work because of that. And you can see it's easily estimated via this embeddings data set. I would like to talk a little bit more about text-to-image embedding interface I prepared. So SIGLIP is one of the models that we have repository of our embeddings. They are all available in our catalog dataset in auxiliary data. And except SIGLIP, we have a few different models. So I can tell you, like, for example, SSL for EO, Dino, DCUR, or MF-ERF. All of them very, very big embedding data sets, around 200 gigabytes at least. And they were created from different data sets from Sentinel-2 optical L1 and L2 level data, Sentinel-1 SAR data, and DEMS. Around 20 terabytes of data for each data set. And this example can show you how in SIGLIP we can, using text encoder, because this one model has it, we can add one query, for example, urban area, sea coast, or deforestation to our text encoder. It can easily access our database and give us a meaningful example on how this actually works. So I would like to show you it in a little demo. So, for example, what I would like you to see is, even though our datasets are just unlabeled satellite images, the model can actually, with embeddings, capture the meaning, not only the labeled value. So, for example, if we try to find a city like London and search for it, it will take like a few seconds to search through whole data set of around 40 gigabytes. It will give us, it can give us actually the city of London, even though it's not in other way described in our data metadata. We could try to search for different city, for example, New York, Paris, or different one. But if you try for not the popular cities like capital cities or big population cities, it will probably give us some random results. But this is only one example. Other way can be something like airports. Yeah, so you can see it actually finds some airports for us. So for example, let's say this one. You can see it's actually the patch that was found on the model in a few seconds is from this satellite photo of Sentinel-2. And all the next ones, similar way, are found in just seconds for huge data set. Other examples I could show you is, for example, events that are not like airports that stay there for all the time, but are just temporal. So, for example, wildfire. Yeah, as you can see, we can't search through whole data set, and in just seconds we have specific examples like fire in Africa found it in 5 seconds. So we can compare easily that our area and what we see on the embeddings photo is different one. So fire occurred only once. I could give you some other examples, like, for example, when you try to use embeddings to find something like something specific, like, for example, White House in United States, it wouldn't be easy to find because White House can be just a building everywhere. So if you try to search for it, it will probably give us something meaningless, so random example photos, because it can know how is it. But if you try to add in DC, which stands for Washington District, it captures it much better, and it actually found area where the White House is built in Washington City. So these easy examples for that, but We can search for other types of, like, for example, mines, petrol fields, or we can try to use it for not remote sensing task, but for example, because it's basically one space matrix for embeddings representation, we can try to ask something that it's for the first view not practical, but it will probably find something that matches the best our query. So for example, if I try to ask for Picasso paintings, you can check how it finds. Yeah, and you can see it found some nice shapes that are probably nothing specific for our analysis, but it can somehow maybe compared to paintings of someone like Picasso. We can try to find for other examples, but the point of this demo is actually show you that without any fine-tuning, we can use model that was trained on random photos. So for example, people riding bikes, and it still captures meaning very well without our additional work. We can just have our database and search through it very quickly, very easily, and capture what we need. Yeah, so I think that will be my part.
Okay, Q&A time. I guess we already answered plenty of your questions, but I still see some, I guess, unanswered, so I'll just go through those. First one, do you have to pay for downloading Sentinel data via API? No, we share public. No, the HTTP download for data is completely free for whole collection of Sentinels for every product type within them. Okay, what foundation models are embedding suitable? I guess it was already covered, but maybe Bartek can take this one also.
Yeah, so I told you that we already have some data sets in our catalog. It is created from 4 big repositories of around 20 terabytes of data each. So it's photos all covering whole planet surface from Sentinel-2 L1C and L2A data. It's from Sentinel-1 SAR data and digital elevation models, another 1 terabyte of data. And all these data sets were used to create embeddings for models like SSL4EO, Dino, Siglip, Decur, MF-ERF, but actually we already adding more data sets from, for example, Alpha-ERF embeddings from Google. And we are still planning to add more models into our repository in the near future.
Okay, thanks, Bartek. Okay, just scrolling down. And can you create a point cloud loss or loss from your data, and how? Geez, I'm not an expert in terms of photogrammetry, but I guess if two for example, Sentinel-2 photos are overlapping, and basically the covering of the same space by 2 pictures, the base of the auto-rectification process, I believe it can be done, but I'm not an expert in this matter, so I'm sorry, but I cannot further answer this question. In case of VM failure, are backups provided, or are they the user's responsibility? Well, we do not support authenticated backups, but our support team is working, I believe, 24/7, and they are very helpful, and basically they are the first contact for you, our users and customers, to reach out to. And so yeah, so in case of any failure, you are not left alone. But of course, also our dashboard, our infrastructure supports backups in form of snapshots, but those are on your request, managed from the mentioned dashboard. Can we download specific bands from Sentinel products as individual JPEG 2000 files or .NET-CDF files? Yes, you can do it with STAC catalog. You can, we'll provide you URL to the CREODIAS STAC catalog, but basically we expose every band of Sentinel-2 and any other Sentinel separately, and you can download it via HTTPS for free, of course. How often are the foundation models updated? Once again, Bartek, I guess. Okay, Bartek will reply to this one via chat. And again, question: in case of VMware, are backups provided? You can do backups on your own via our Horizon dashboard by snapshot utility, but of course, in case of any damage, our cloud and support team is there to help you. From SAR data, I guess this question maybe has been cut in, I don't know this. Are Sentinel-2, Sentinel-3 co-registered images available? Again, this one will be replied via chat. Will the recording really be shared? Yes, it will be really shared. Do you offer free accounts? Yes, we provide 250 euros for start with our infrastructure, but again, product download is completely free. So if you don't want to use our cloud infrastructure, but you still want to download products, you can of course do it for free. And I guess that's almost all. That's all. Okay, I see that my colleagues are still replying. The ones unreplied, but that's okay. I guess we can still have 2 minutes for you. If you have any questions, please feel free to post them via chat. Okay, I do not see any other new messages. So yeah, please remember our colleague will share the survey with you in a few seconds via chat. Please, if you would be so kind to fill it and give us our opinion. If you are satisfied with the webinar, then let us know if there are things that we can do better, or for example, if there are collections of data that you think that we should also provide our users with. So for example, the co-registered photos of Sentinel-2 and Sentinel-3. These are great things to, this is a great feedback for us, really, and please be so kind to share it. And yeah, big thank you from me. And I think we can end. Once again, thank you, and bye.